Bond order, length, and energy, as well as atom size, are concepts that are really intertwined in terms of their effects on the structure and shape of molecules. The length and strength of covalent bonds is critical to understanding the shape and chemistry of molecules. Molecules undergo chemical reactions at places where their bonds are weak, which is why it's important to know where those are. They will also undergo reaction where vulnerable atoms are exposed by the molecular shape. So if an atom is trapped inside the molecule, it's going to be harder for another chemical to get in there and react with it. If, on the other hand, it's hanging out on the very outer edge of a molecule, it's going to be much easier to get at. We need to understand how bond order, length, and energy are related because this is how you learn to recognize patterns of chemical reaction. So some definitions. Bond order. This is the number of electron pairs shared between two atoms in a particular covalent bond. So looking at a carbon-carbon single, double, and triple bond, the order goes 1, 2, 3. All you need to do is count the number of lines we've used to represent the bond. Each of those lines represents a pair of electrons being shared by the two atoms. Bond length is the distance between the centers of two atoms sharing a covalent bond. So if you and your friend were standing arm's length apart, your bond length would be the distance between you. If we look at our carbon-carbon bonds, we can see that these are measured in picometers, so these are 10 to the minus 12th meter. And for a carbon-carbon bond, for example, the bond length is 154 picometers. Bond energy is the energy cost required to break 1 mole of a particular kind of covalent bond. Remember that bonded atoms are more stable than free atoms. They are lower in energy, so we always have to pay energy to break a bond. These energies are given in kilojoules per mole, and for example, a carbon-carbon single bond has a bond energy of 348 kilojoules per mole. Now you may have been looking at these tables on the slide and beginning to pick up on some patterns as to how these three concepts are related. Let's take a peek. There are two factors that affect bond length and energy. The primary factor that will affect it is bond order. Higher order bonds are shorter and have higher bond energies. So as bond order goes up, bond length will go down, and bond energy will go up. Let's take a look at those carbon-carbon bonds again. So we've got carbon-carbon going from order 1 to 2 to 3. As we go from 1 to 3, the length of the bond shortens from 154 picometers to 120 picometers. Similarly, as we go up in order, the energy increases from 348 kilojoules per mole to 839. Now, this bond order effect is the stronger effect, which is why I say it's primary. The secondary effect is from atom size. It also affects these factors, but not quite as strongly as bond order does. Bonds between larger atoms are longer and have lower bond energies. Again, imagine trying to tether together a couple of squirrels versus a couple of elephants. As atom size increases, you will see bond length increase and you will see bond energy decrease. So take a look here. We've got iodine-iodine, bromine-bromine, and chlorine-chlorine bonds. The size of an iodine atom is 133 picometers, while the size of a chlorine atom is 99. So we're decreasing in atom size as we move down this table. As those atom sizes decrease, so does the bond length. An iodine-iodine bond is 266 picometers long, while a chlorine-chlorine bond is only 200. As the bond length decreases, the bond energy increases. So we have our long iodine-iodine bond with a bond energy of 151, while our shorter chlorine-chlorine bond has a bond energy of 243. But now there's a last consideration: resonance effects on bond length and bond energy. When two or more resonance structures are possible, the actual structure of the molecule is an average of all resonance structures, weighted by their stability. So the most stable resonance structure will have the most influence on the molecular shape. This means that the length and the strength of the bonds within the molecule lie between the values for the specific resonance structures. Let's look at an example. This is a benzene molecule, C6H6. And inside the ring, it's got a pattern of alternating double and single carbon-carbon bonds. We can draw a resonance structure of benzene where the double bonds have been moved to the opposite carbons. These two structures exist at the same time. If we look at just one of these structures, we would expect to see carbon-carbon bonds with a particular length and energy, and carbon-carbon double bonds with a particular length and energy. But this is not how benzene actually exists. In real life, benzene's carbon-carbon bonds aren't a pattern of alternating single and double bonds, but rather a ring of single bonds with this shared ring of 3 pairs of electrons on the inside. So it's more like having 6 1.5 strength bonds. In real life, if you measure the benzene molecule, you find that its carbon-carbon bonds are 140 picometers long, and they have a bond energy of 518 kilojoules per mole. If you take a look at our single and double bond values, the length in the benzene ring, the actual benzene ring, lies in between our two choices for length, and the energy also lies in between the two possible values for energy. So when you have resonance structures, you should expect to see that the actual values lie in between the extremes possible from different specific resonance structures. So there you go. That's our overview of bond length, bond order, bond strength. I'll see you guys in class.